This is Tundra over here with the muskox and the Arctic hares. This is actually a deep, deep fjord full of water with a little bit of ice floating on top. And the main ice sheet is way up there coming towards you. And I'm going to show you two pictures. One here of the ice with water under it, and one up there of the ice that doesn't have water under it. And the one here, there's a seal. Okay, yes, there's water under there. They actually do oceanography with these seals. They put instruments on them. They swim around under the ice in the water. They come back. The instruments telemeter what they measured. And then variously up at the head, here we go. The seal was down here. This used to be filled with the spatula, the flying buttress, the ice shelf. And then it broke off and it left this cliff. This cliff is 30 stories high, right? 330 feet, 100 meters. Below, it's 9 times that. So this thing is 2/3 of a mile high in total. For scale, there's the Lincoln Memorial, to scale. If you remember, Lincoln's big, and he's that little thing in there. And the next picture is here, right? And so there's the Lincoln Memorial, and there's the cliff. When I took this picture, I had this remarkable experience. I was in Greenland with 10% of the Senate. We had 10 senators on a long weekend, and we're showing them Greenland. We are in a helicopter. We are flying along the front here, and the pilot says, "How close do you want to get?" Now, I want you in your mind for a moment to think of about a 30-story building down in Chicago, and think about looking up at that 30-story building and seeing a 10-story high crack. And then you say, how close? Do you want to go walk under the crack and look up to see what it's going to do? You know, and I said, these are senators, maybe pull it out a little bit. Right? This is a cliff. That is as high as you can make a cliff of ice because it's obviously just about ready to break. Okay? And I'm going to show you what it does, right? So this is some pictures of it breaking. So here we go. This is the 30-story high cliff. There's the Lincoln Memorial. This is a piece breaking off the front. The seal was down here in this water with ice on top, okay? And this is rolling over as these pictures were taken. That's 30 stories. You are going to see a 50-story high splash. Water that splashes 50 stories. What's this thing? I mean, this is just fantastic. Running it backwards now. I could do this for a long time, right? This is just fantastic. You can see the bottom of the glacier rolling over. This thing makes earthquakes that you can hear here. Magnitude 5-point-something earthquakes when it breaks off, right? And so now what does it do? It breaks, it waits, it breaks, it waits, it breaks, it waits. But it's almost ready to break all the time. If that cliff were higher, it would break faster. So we're just about done. This is Antarctica again. The flying buttresses are this white. The cream over here, the gray, is if you melted the ice, it would have land under it. You can't make icebergs there. The color, you can make icebergs and you can raise sea level. The bottom is below sea level, so you can make icebergs. The top is so far above sea level that it won't float. And this thing in here is called the Bentley Trench. It was discovered by Charlie Bentley of the University of Wisconsin. And what you'll notice, if you started unzipping this, you would get a cliff that's twice as high as the one in Greenland. And then it would be 3 times as high, and then it would be 5 times as high. And higher cliffs break faster. And if you started unzipping this, everything in color here goes away. And what does that do for sea level up here? It's about 15 feet. And when we put the physics of that in a model, it says that once it gets hot enough to make Sarah's lakes, once it gets hot enough to start breaking that thing apart, that you get that sea level rise in decades, not in centuries. And so we're expecting by the year 2100 about this much sea level rise, and the usual report is it could be that and it could be that, but if West Antarctica breaks, it's up on the next floor. Okay? And that is a metaphor for a lot of this story. We have an estimate of what global warming will do to us. And there are costs associated with that, and if we take wise policies, we will be better off. And the estimate could be, it could be a little better than that. There's real science, real uncertainties. It could be a little better than that. It could be a little worse. But there's nothing in sea level rise that's fantastically better. Sea level fall would mean you'd had to dredge all the channels. But it could be fantastically worse. And we keep seeing a little better, a little worse, a lot worse if we don't use our knowledge. And people say, aren't you uncertain? And you say, yeah, and I'm really worried about that. Because it could be a lot worse. We could break things we care about very deeply. And so the uncertainties being a little better, a little worse, or a lot worse, the less you trust the science, the more worried you should be about global warming. Because we really are doing something that really will change the world, and we're assuming it won't be a big deal. But it might be, because we've got all kinds of valuable things we could break. And so, the different talk, and I'm going to finish on this note, what I told the high school students this morning. We humans have spent our entire existence burning things for energy, breathing the smoke, running out, having crises, having government interventions, and trying to find something else to burn. We burned whales far faster than they grew back, and we almost killed off all the whales. We burned trees to the point that basically everything in the East was deforested. And then we had all kinds of government interventions. Don't you dare burn your tree. That's my tree. Let's fight over it. Because they were so scarce because we burned them so much faster than they grew back. We are burning fossil fuels 1 million times faster than nature saved them for us. The trees grew back in 100 years. The fossil fuels will grow back in 100 million years. But we finally are at the point that those wind turbines are undercutting the price of energy from the coal plants. We finally are at the point where we know how to build a sustainable energy system looking forward. And we know, and this is the whole picture. This is the IPCC. This is the National Academy. If we use our knowledge efficiently, with respect for where we came from and appreciation of the value of fossil fuels, compared to business as usual, if we use our knowledge, we get a bigger economy. We get more jobs. We get greater national security. We get a cleaner environment, and it is more consistent with the Golden Rule. We have always used our knowledge. We have always taken what came back. We have taken what's been invented in these halls and many other halls, and we've applied it to make ourselves better off. This knowledge doesn't tell us what we have to do. It tells us what we can do. And we can build a better world. And so I'm going to point it out that we could do this. We can power essentially everyone. We can farm energy the way we farm food. And what's possible at the end of 30 years of serious effort is essentially a sustainable system that goes forever. And it's a system, and I'll leave you with this. I took this picture in Greenland a few years ago. It can leave us with a world that really does have icebergs and rainbows. I thank you, and I will happily take questions. Oh. Yeah. Wow. Yeah. Okay. Oh, thank you. My goodness, is wonderful. So we are going to do questions. There are microphones that will be coming around. So if you have a question, wave, and we will try to get you a mic so that you can ask it. And we will celebrate the first brave person who asks the questions. We have one mic down here. We've got one over here. Here we go. Great.
I've heard that the higher concentration of CO2 makes us duller, but that isn't my question. All those graphs you showed of the warming and the cooling and all that, do we have any idea how high the sea level has gotten in previous cycles?
So probably the previous warm period, the sea level was sort of probably about 5 meters higher than modern, and it was only a little bit warmer. We keep coming up with an answer that a little more warm sustained gets us a lot more sea level, and that is worrisome. In fact, the long-term steady-state sea level associated with modern CO2 might be 15 or 20 meters above modern. This is not good. So, yeah.
Sorry, one more thing. It looked like on one of your graphs, as you get close to today, we're seeing all that more warmth than the previous.
We are getting more warmth, and it is heading up, and it is real. And every data set, if you average over the wiggles, shows warming. The NOAA data show warming, the NASA data show warming, the British data show warming, the Berkeley data with their funding from fossil fuel corporations, among others, shows warming. The satellites show warming. The ground is getting warmer. We're getting less river ice. We're getting less lake ice. We're getting less seasonally frozen ground. We're getting less permanently frozen ground. We're getting less seasonal snow in the warm seasons, and we're losing ice from the glaciers and the ice sheets. Also, almost all the phenology changes where things live and when they do things are in the direction of warming. So yes, it is getting warmer.
Well, thank you very much for your presentation. You're very good at communicating the information that you learned.
Well, thank you.
Yeah, so is there going to be a safe place on the planet?
Is there going to be a safe place on the planet? So yeah, so what do we get? We get more floods and more droughts. The biggest storms can get bigger. The sea level comes up. If you're in central Canada, a little more drought, but you're not going to die. We're weeds, right? Humans are the greatest weed that nature has ever invented. We'll be here. Well, if we do nothing, by about 2100, there will be, if we keep emitting a lot of CO2, it starts to get to the point where there will be places on the planet that are fatally hot. So if you are sitting there drinking water with the wind blowing naked, and you would die of heat exhaustion. And long before that, it gets really hard to work outside in a lot of places. And so, yeah, the hot places sort of get screwed over.
What are some of the cooler elements you found with the space dust?
Okay, so the space dust is, what they usually look for is iridium, sometimes platinum, what have you. But there just isn't that much of it. And people have gone back pretty far looking for it. And obviously, meteorites do interesting things locally. The big one, 66 million years ago, they did the dinosaurs in. That was. But it turns out probably that was mostly climate, and it was mostly a nasty accident. So it turns out that what the meteorite did was hit off the Yucatan, and it hit into rocks that were really rich in sulfur. And they were rocks that were also really rich in carbon. So what does it do? It blasts stuff around the world. The stuff falls back in. It gets hot when it's falling back in. It sets a fire, and it burns a whole lot of the world. And then after that, because it blasted sulfur up, the sulfur makes sulfuric acid. The sulfuric acid makes drops in the stratosphere. The drops reflect the sun, and it gets ridiculously cold, and everything freezes. And a few years after that, when the stuff falls out, there's extra CO2, and now it gets hot. So if you're sitting out there on the land surface doing what you do, and all of a sudden you get burned, and then you get frozen, and then you get fried, right? And if it had hit other places, it probably wouldn't have killed the dinosaurs. It really probably was because it happened to hit rocks that were so chemically interesting. So the chemists are hanging around here. You win again. But
Thank you.
Thank you.
Hi, I'm just.
Sorry, you go first.
Oh, thank you. I'm just curious, what's the most interesting position you have heard from someone either in your field or a closely related field that differed from yours? That actually made you think, like, maybe that's a possibility that there's an alternative thought process?
So I've been at this long enough that I have come through the era when people who were skeptical of our accepted understanding had real points. And we'd ask about, is the band saturated? And we'd ask about, will there be a cooling kickback from the warming? And we'd ask about a whole bunch of other things. Is there a chance that the cloud feedbacks are negative rather than positive and we won't get as much warming? And we've had real, honest-to-goodness questions, and they've been answered. And what I find more and more is that what is classified as the skeptic world, it doesn't have anything anymore. And they're going more off into sort of craziness. I deal a lot with temperature goes up and down because the sun gets brighter and dimmer. The El Nino goes to La Nina and back. The volcanoes block the sun or it doesn't. And temperature goes up and up and up because of CO2. And if you add up and down to up and down to up and down to up and up and up and up, what do you get? And what we hear every time a wiggle turns around, they say, you guys are evil liars, there's no global warming because it's going down. And this is just intellectually bankrupt. And we have known how to do statistics of curves to ask whether it's significant since the Guinness Brewery figured it out. The student t-test was published under a student because the fact that Guinness was using mathematics and statistics was a business secret. And we've known this for a very long time, and people are spouting nonsense about it. We still hope that maybe there's some chance that the transient climate sensitivity will be a little lower than we thought, although the equilibrium climate sensitivity is a little higher because you pump all this heat into the deep ocean, and so maybe we've got a few decades before it gets worse. And the ice sheets still have huge uncertainties. The biological responses still have huge uncertainties. To be bluntly honest, the big ones are how we respond. Do we tip societies into disaster, or do we build resilience into the society so they can get that? There's this wonderful story, right? So it's a wonderful, horrible story. We made drought more likely in the subtropics. The expansion of the subtropical dry zones is a robust conclusion of climate models because you're driving the Hadley cell harder. And that is showing up in places such as the Middle East as a greatly increased risk of drought. Drought hit the Middle East. Did we cause it? We made it 2 or 3 times more likely, and it happened, right? We loaded the dice to come up drought came up. Israel did not have a civil war. Lebanon did not have a civil war. Syria had a civil war. It is well accepted that the drought was an important forcing. It was a stressor of a very, very unhappy place that was Syria that tipped them over the edge into the civil war. And so one can look at that and say, we made the drought more likely, the drought happened, that kicked Syria. And you can look at the future where all the projections have a lot more drought in Syria and Lebanon and Israel in the future. And you can say, well, that's a terrible thing. Or you can look at it and say, Israel and Lebanon did not have a drought, how did they survive? Where do you build the resilience into a system so that it can survive the threats that are put at it? And across the board, if you ask, should we put our effort into stopping global warming? Should we put our effort into building resilience to deal with the impacts? The answer will always be yes, you do some of both. And you never will get one or the other as the only answer. You will get adapt to the coming changes and minimize those coming changes in a way that works best. Okay, yes?
You mentioned that weirdnesses aren't recorded in the ice cores. How do you think our current time will be recorded? Do you think it will change how the ice cores and the
Right,
patterns
so
have been?
presuming we don't melt the ice, Lonnie Thompson, who was here a few years ago, his records are melting now, so the places that he took cores are going away. Presuming we don't, the human's fingerprint is very, very clear. And it's clearing a whole bunch of things. The one, I'll tell you one, which is lead, plumbum. And if you go to Greenland, you take an ice core and you look at the lead concentration, there's actually a little blip in the Roman times. And we're pretty sure this is dust from lead mining to make plumbum for plumbing for the Romans. And then it goes back down in the Middle Ages. And then when we start into the Industrial Revolution, lead just starts going through the roof. And it goes up and up. And then we get to leaded gasoline and it goes boom, and it goes way up. And then at some point we said, you know, lead is a poison and it makes people stupid and we should clean this up. And it comes back down. And so there's this history of a blip and then this huge rise, and then we get rid of most of it. And that's there, and it will be there as long as the ice sheet is there, and you'll put your finger on it and say, wow, that's crazy, something happened there. But you'll also say, you know, when we agree to clean it up, we can. And that's pretty cool.
Okay, we have time for maybe one more quick question, if someone has it.
Can you speak to the idea of tipping points like melting permafrost?
Yeah. So a lot of my career has been looking at the things that could surprise us, looking at the tail risks, looking at the black swans, looking at the tipping points. And that is one of the reasons why the uncertainties are loaded the way they are. We're assuming that nothing will tip. That's the best assumption we can make. We are cautiously optimistic that except for West Antarctic collapsing, that we will miss the physical tipping points. The North Atlantic will change slowly, not fast. The methane will come out of the permafrost slowly, not fast. There's an immense amount of carbon in the permafrost, but right now it's frozen, and melting the ice in the spaces takes a little while, and then letting the biology turn all that dead stuff into methane takes longer. So we're fairly confident that that won't tip. We're worried about some ecosystems. If you make it really, really dry in the Brazilian rainforest, will it burn and come back as a savanna rather than a Brazilian rainforest? That's one of these questions that you worry about. And then we're really worried about the human tipping points. Syria melted. And Lebanon didn't, but Syria did. What is it that pushes people over the edge? And what are the, you could find learned people who will suggest that the refugee crisis from Syria can be seen echoing into things like voting on Brexit or voting on how much people like immigrants in the United States, right? These things cascade, and we probably have all kinds of tipping points in our systems. And how we deal with this. I will finish with a call here. I'm a physical science. I love physical science. I want lots of students to take math. I want lots of students to take physics and chemistry and so on. But we're going to need people who know how to make people work together. We're going to need people who understand how to build resilient systems. We're going to need people who understand how to get food to where it's needed without killing the local farmers. And I think that you're among the places that generates those people at a rate which is higher than you should be. And so I'm going to sing the praises of physical science, but be very clear. We need people in social science. We need people in business. We need people who have a commitment to using their knowledge to help. And if we go home and pretend we're stupid, we will lose. And that's exactly what you were not doing. And I am very happy to have played a little tiny role here. So thank you.
Thank you very much. Very well-deserved applause for Dr. Ali. I said he ignites. Would you agree? That was an amazing presentation. So thank you very much. And at this time, we do have to close out. There will be a book signing up in the lobby. And then for those of you who have purchased tickets for the dinner, that'll be next door in the Center for the Sciences. So thank you so much for coming, and have a good evening.
Okay.